So good afternoon, everyone. I'm Sharan. I work for the JuliaSim team at Julia Hub, where today I'm going to be talking about surrogatizing dynamic systems using JuliaSim. There's a new product which is called Digital Echo, which is in fact demoed by Chris in his sponsor talk, but I'll be talking about it in more detail today. So let me just briefly discuss the agenda for today. So I'll start off by motivating the problem. Why do we need to surrogatize? Then what a surrogate is. Then we'll talk about reviewing the current prevalent surrogate generation pipeline. What do people do today? And then I'll go about introducing Digital Echo, which is our solution to this problem. And then I'll go on to explain some examples using Digital Echo. So to start off with, imagine you're a chemical plant engineer, and this is the chemical plant you're in charge of. And you need to tune the parameters of this chemical plant on a regular basis depending on the prevalent conditions, and the required output from the plant. And for a plant like above with a sufficient number of complexities and sufficient number of subsystems which have their own independent physics going on, it's very computationally intensive to simulate such a system. Even if you have the physics of the system kind of written down in code, to simulate such a physical system takes forever. It could be in the order of hours or days even. And this is prohibitively expensive, and it negatively impacts the productivity of the plant. So this is what we are trying to change, right? We are trying to make such a chemical plant engineer much more productive on the day-to-day basis. So here, what we see is the power of speed. So the first block you see is kind of a representation of a single simulation being run by a single chemical plant engineer. The second one is, say, a group of such simulations. It can be either run by a same person for multiple different parameters, or it could be like different, like a group of people running different experiments to decide parameters on. And as you can see, as we kind of scale it up, we are able to So once we scale it up to a larger scale simulation where we are able to do hundreds of such simulations at once or in a short span of time, we are able to kind of liberate that chemical plant engineer into doing all this experimentation on his own, or do it in a much shorter period of time. Instead of in a matter of days or hours, it could be in a matter of like seconds even, right? We have had real world problems which we have solved, which take an order of magnitude, several order of magnitudes less time after the speed up using a surrogate. So yeah, the main reason we want surrogates is faster workflows. And faster workflows are enabled by faster such components. So each of those individual components have their own complexities. But if we take the slowest component and speed it up, that itself saves a lot of time. And what this enables is faster parameter optimization or faster control design, which is very crucial in any research or a production setting. So I keep talking about surrogates. So if someone isn't aware of what surrogates are, they're essentially machine learning models of physical systems. They are fast but approximate models for a given physical system. So when I say approximate, they approximate pretty well, and they're very, very fast, right? And I'll demonstrate some examples soon. So let me first discuss the current pipeline, which is often followed by the industry, and the problems with it. So whenever I say a machine learning model, obviously you need a lot of data. So that means generating the data set first from the physical system. This essentially involves training it with different parameters, different control settings, and is a very hard problem to solve because how do you know what kind of control systems are required, right? And it's a very expensive, computationally and like technically, it's a very hard task. And once you have the data set, the next thing you want to do is pre-process it, because that's something which is often non-trivial, because based on the model you're dealing with, you will have to pre-process it in a certain way. And that is always an expert thing to do. You need a machine learning expert to do all of that. Often, each of these individual steps which you see above are often handled by different teams, and they have to kind of work in sequence, and it's very hard to parallelize these jobs. And that kind of slows down the entire process of surrogatizing a lot. And that would basically bring down the productivity of the entire company by a lot, because each team is waiting for the previous team to get their work done, and it's a never-ending thing. And even after you have a prepared data set, you have to choose and configure the model and tune it, which is not at all trivial. You again need a machine learning PhD for it. And then you want to train it. Training involves HPC. It involves kind of parallelizing it. It involves GPUs, which is all, again, a big headache, right? Then we want to validate it and deploy it. Deploying, again, involves a lot more technicalities, which often companies do not want to deal with. So what our pipeline, the Digital Echo pipeline, enables is it gets rid of the most painful processes, which is pre-processing the data set, configuring the model, and even training the model. All of that is automated for you. So we have our pre-processing pipeline, as well as, which is followed by the training pipeline, where we configure the model for you. And the training also happens in an automated way on the cloud by using all the resources available, right? As many GPUs as needed, as many CPUs as needed, right? And that is what makes this process faster, and even for a surrogate engineer. So yeah, so to enable all of this, we introduced Digital Echo. It's essentially an automated framework for generating accelerated, high-fidelity digital models that can reproduce the behavior of your simulator process. So when you use the Digital Echo product, the first thing you will want to do is kind of specify what kind of data you want to generate, right? And that essentially involves telling what kind of parameter space you want to work in, or what kind of control space you want to work in. And that's all you need to do, after which the rest of the steps are kind of handled by the pipeline. And you only need, like a domain expert only needs to care about what they are aware of. They are aware of the parameter spaces. They are aware of what kind of controls they deal with. Everything else is, they don't need to worry about it at all, right? That's the whole point. No machine learning expertise is required to get this done. And it scales in various kinds of surrogates, both full model and component model surrogates with a single API, right? Let me show you a demo, which was, I think, already discussed in the sponsor talk, but I'll explain it in slightly more detail. So what we are trying to do here is we are trying to surrogatize a pack of batteries, a pack of electrical cells, which makes a battery. And as you can see here, these batteries are often used in electrical vehicles nowadays. And it's very important that you get accurate predictions of the charge cycles so that your car doesn't stop halfway, right? And as you can see here, the left-hand side is essentially without a surrogate. If you try to simulate this whole process, it takes very long time. It's like the car is not even moving. But when you look at the right-hand side, it's with the surrogate. It's just trying to demonstrate the speed of the surrogate. And in this case, it's the speed makes it like order of magnitude difference in how you want to deal with that physical system. So Coming to the properties of digital echo, right? Often when we say a machine learning model, we say like it turns out to be some sort of a neural net, which is fully black boxed, and there's no sometimes there's no theoretical grounding to any of this. So that's the first thing we were thinking about. How do we make sure that people can trust this system, right? The idea behind digital echo is that it relies on well-studied theory of topological conjugacy, which essentially means that there exists this alternative topological space where the dynamics are easier to kind of simulate, but at the same time, you won't lose out on much of the information, right? So we essentially map our existing space into this topologically conjugate space where it's super easy to simulate, super fast to simulate. The system is not that stiff anymore, and that makes all the difference. This is what has enabled us to get the state-of-the-art method in SciML in terms of both accuracy and performance, that is speed. Right? And the second most important thing here is probably we are tightly integrated with all sorts of standard modeling tools. So to start off with, the first thing we want to support is obviously modeling toolkit within Julia. And this allows us to make use of the wide array of SciML solvers, like these high performance solvers, which are proved to be great. I think if you have attended Chris's talk earlier today, we know that these solvers are better than the defaults found in most other systems. And we make use of it, right, when we are in the SciML world. And a lot of it is built on top of modeling toolkit, and it has first-class support for modeling toolkit. At the same time, we know that not all the people who want to use this might be familiar with modeling toolkit or Julia. So what we also enable is to import these physical models from outside by supporting the FMI, that is functional mockup interface. And this enables us to kind of import models from any other external simulation device which supports FMI, which is most of the good ones kind of support that. So good ones support that. So you can be sure that you'll be able to use this product irrespective of which kind of ecosystem you come from. And another thing is that we can integrate these fast surrogates back into the simulation environment, right? As a drop-in replacement for your current systems. So you have a current system which you know works well. It's a physical system, but you know it's very slow. So what you can do is you can create an FMU out of it and just put it into our product, and it will give out another FMU, a faster FMU, an approximate FMU, but a very fast FMU, right? And this can be a drop-in replacement for that existing subcomponent. And what this enables is that you don't have to change all of your pipeline at once. You can go about experimenting with just one component, which is the most painful one. And that way, you can slowly kind of convert your workflow into a faster one, right, in a step-by-step manner. The third thing is it's fast. It's extremely fast. It's faster than anything which is out there right now. And it's because of this theory of topological conjugacy, and we are able to find a right mapping. That's the main thing here. We are able to find a right mapping onto this easier space, easier to simulate space, and this is what makes our surrogates blazingly fast when compared to the original simulation. So let me discuss another example, which is the brusellator. You might have heard of brusellator if you come from the SciML world. It consists of essentially two partial differential equations, which represent two different species, and it's considered a very stiff, very complex model, and it's often used as a benchmark for various solvers. And it used to be unimaginable to think about surrogatizing this because of the stiffness of the system. But we have been successfully able to surrogatize even such systems, even such theoretically complex systems, and produce order of magnitude of performance gain. So here Okay, we are able to speed things up, but that's not everything, right? What do we do with the speed? So we need to think about applications using the speed, right? And one of the major applications which I discussed earlier is parameter estimation. And we are able to do that with digital echo on Brusselator very fast. If you see the right-hand side, you can see the speed at which it's able to fit to the parameter estimation is able to fit and like converge. And this is all enabled because of digital echo, right? As I said, you can use the digital echo as a drop-in replacement for original model. That means that you can use it as a drop-in replacement for parameter estimation, control tuning, all of that, right? Yeah, this is something which I discussed already. So essentially, because of all the speed up, you're able to kind of democratize a lot of these simulations. You don't need to have in-house crazy amount of compute to run things in parallel and still take days to simulate them. You can do all of that on the cloud while using the best of infrastructure, and you can train using the best of infrastructure too. So let me delve into slightly more detail into what a workflow looks like for an actual developer now. And so as you can see here, the first part is essentially, most of the work is essentially data generation setup, right? That's the only thing the user really needs to worry about. That, okay, what is my parameter space which I'm interested in? What kind of controls am I interested in, right? And what kind of time span am I interested in surrogatizing over? If you have this information sorted out, then you're good. Then we take care of running parallel jobs, thousands of parallel jobs, and generating thousands of data samples which are required for the surrogate, right? And all of this is done by using the Julia Hub platform, where we are able to run these massively parallel jobs on Julia Hub in a much more scalable way. And once the data generation is complete, we have all sort of visualization tools to help you kind of see how the data looks like. Is it covering the spaces you really want it to cover, right? You can have phase space plots, you can have trace plots, and we have an entire visualization suite dedicated for that, right? Apart from that, in this example, we also show how you can kind of validate this in both open loop and closed loop setting. Open loop is hard, but it's not that hard. But closed loop is often known to be very hard to actually allow. What I mean by closed loop is essentially we test this surrogate on a controller, which takes back the observables as the input, right? The controller decides the next set of inputs using the previous observables. And all of this means that we are actually learning the underlying dynamics. We are not trying to curve fit like most machine learning models do. We are actually learning the underlying physics or simplified versions of the physics. A reduced order model, it's a reduced order model where we are trying to learn the physics underneath. And that is what is enabling us to achieve all of this accuracy and while retaining the performance, right? Or while improving the performance even. So one other thing to note here is that some of these plots, I think the third plot here is this. Yeah, the third plot here, you might notice that it is more of a qualitative fit for a transient region. So what the kind of approach we are taking towards this problem is that often engineers are very concerned about the steady state of the system, that they want to make sure that they get the right steady state. But the transient behavior before attaining the steady state is not that much, it's not quantitatively important, it's qualitatively important. So even if in some crazy transients where we can't fit the quantitative behavior, we make sure we fit the qualitative behavior, right? So that way, like a real world application of this would be that if you have a controller you're trying to tune, if it's unstable, you'll be able to detect it, right? That's the whole point of it. So the first example was using an ODE problem source. So as I said, we allow importing models from various sources, including ODE problems from MTK. And the second example you see here is from an FMU source, right? And the API remains almost the same, right? There's the only, instead of plugging in an ODE problem, you'll be plugging in a path to an FMU, right? So that way, your workflow is unaltered, irrespective of the source. And you can see here that it's again the same thing, where you specify the data gen, and the training is taken care of. Also note that you might, it might seem that these are toy models, couple clutches, but these are only to demonstrate so that you can quickly run this on our platform because they are super easy to simulate. We have tested it out with all sorts of more complex systems like batteries and HVAC. So apart from having a MTK source or a FMU source, sometimes you already have real world data. So we have had clients come to us who say that, okay, we already have a data set collected from real world trials, and how do we model this, right? So we also allow for that. So as long as you have data set in a certain format, which is specified clearly in our docs, you're good to go. You can model that physical system. Even if the physical system is completely unknown to you, it doesn't matter. You can still model it comfortably. So do check out our docs. This is all live as of a couple of days ago, so it's actually part of the free tier of Julia Hub, so you can go out and play around with all of this. And do let us know what you feel and if you like it. And if you are interested in any specific aspects of this, please reach out to us at the booth. We will be open to any questions. And any questions now too.
So how does this integrate with model analysis tools, such as like sensitivity analysis? So can you still find out about physical parameters despite making a surrogate of the actual model?
Sure, that's something which I was talking about with the parameter estimation. So yes, any sort of model analysis tools, it's a drop-in replacement for the original system. So you can do any sort of analysis with this too. And so say parameter estimation, you can do that. Also, we have in-house such analytics tools. We have Model Optimizer, which I think is separately being presented. And we also have JuliaSim controls optimizer, which is, again, a control tuning framework. And all of that supports digital echo. But also another way to look at it is that even if you get it from an external modeling tool, then you can still convert it to an FMU and go back to your analytics tool of choice. You don't have to stick to our thing. If you're more comfortable with something else for now, go ahead, use it, right?
I think that the key thing is that a feature that's coming is not 100% done yet, it's like 1 month away or something, is that these will be outputting the models as modeling toolkit models themselves. So essentially you have slow modeling toolkit model come in, surrogatize, fast modeling toolkit model come out, right? And that then kind of completes the loop to make it very easy to integrate everywhere. Not 100% done, there is a hiccup there, but it is the next thing to do.
And yeah. Okay. There is a limitation. So one main limitation is that, as I said, sometimes when your signal is super noisy, you only get to fit it qualitatively, right? And the steady state is, however, achieved. Like you can attain the steady state. And yeah, apart from that, so yeah.
There is one major limitation to mention, right? And the limitation is that this, as a surrogate methodology, is a convergent methodology, right? It's designed in such a way that, if you think about the surrogate problem, you have a simulator that's effectively generating you data whenever you want. And so if you set this problem correctly, you should be able to have an
Yeah, so the amount of data you need varies from problem to problem. And the kind of diversity of the data generation is something which only comes with a large amount of data unless you specify it perfectly, right? Yeah.
Do you have examples with the effects because the SSDs has it twice quite high times of the supports, not that fast dynamics. And also usually H-like states are not that fast.
Mm-hmm.
Do you have examples for the quick dynamics?
So two-phase flows has a phase change that happens in the dynamic that is 10 to the 10 so 10 orders of magnitude larger than the standard dynamics of other components, and we show that that's the case here.
Yeah, another thing which is good to mention here is essentially there is an aspect of how fast your dynamics are, and you can tune your model for that. So if you know beforehand that your dynamics are super fast, you can make the model look at it in such a way that there is a time constant involved where you can tune it to capture even a super fast dynamics. Yeah.
There's also a battery example where the current is oscillating.
Yeah, so the battery example is, yeah. So if you look at it here, you can see how fast the dynamics are, and it's still able to capture it.
No, that's the current, that's the output.
Yeah, this is the current. So you can see the dynamics are pretty fast, and it's still able to capture it. And sometimes, even when the transient nature of the thing is also captured, right? Any other questions? Yeah.
Is this able to handle like dynamical models where like depending on the parameters regime, like it's very different behavior? I guess like the classic example is like low Reynolds number flow versus high Reynolds number flow.
Mm-hmm. Yeah, that should not be a problem. Yeah.
Well, but the data gen would have to explore both regions.
Yeah. So the data gen is responsible to kind of, explore all sorts of dynamics. That's why those phase plots which you see, which you saw earlier, are basically, the purpose is to aid that, to make sure that you know that all the phase space which you are interested in is actually covered so that we can capture the dynamics there.
When we create surrogate models in like company work, we find that the quality of model and the speed of training varies enormously with the choice of the architecture.
Mm-hmm.
Is that something that you've kind of considered in your work, or you've just chosen one you think is good for you?
Yes, we have experimented with a ton of different architectures, and what we were aiming for is not just training speed, it's about whether it's able to generalize, whether it's actually able to capture the dynamics with a minimum number of parameters. You don't want to just give it a lot of parameters, it will just overfit, right? And we also are trying to avoid stuff like recurrence, which are often super expensive to train. Those sort of things are being avoided at all costs. Yeah.
I mean, and there's also some other tricks going on with things like, if you know like reservoir computing techniques, right? It can help make the optimization process not as optimization, right? So there's other tricks going on involved. But I think the key thing though is to meet the data gen, right? Pretty much any architecture can do well if you give it the right data. And and by taking the main difference that we've done this year with the surrogates is taking control of the data gen process and saying, we want to make it that way. We force the exploration of the rate space to build a data set that we know will work. And that's really the biggest key difference.
I guess that's it. Thank you.